GD. In the last class we discussed one advanced control scheme, that is cascade control scheme, and today we will start another scheme, that is constraint controller or override controller. So, today we will discuss override control, and it is also called as constraint control. During the normal operation of the plant or during the startup or shutdown, some abnormal situations may arise which lead to the destruction of equipment and operating personnel. During the normal operation of the plant, or during the startup or shutdown, some abnormal situations may arise. Some abnormal situations may arise, or some dangerous situations may arise, which lead to destruction of equipment and operating personnel. Which lead to the destruction of equipment or operating personnel. And in these situations, a special type of switch is used. In these situations, a special type of switch is used. One switch is like HSS, high selector switch. High selector switch. This is one type of switch which is used in abnormal situations, and this switch prevents to exceed the upper limit. It prevents to exceed the upper limit. Fine. In every operation there is a certain limit in terms of upper limit and lower limit, that should be ensured. So, we can say that this upper limit is a constraint. Fine. Therefore, the name constraint controller. Another switch is also used, that is LSS, low selector switch. Low selector switch, and it prevents to exceed the lower limit. It prevents to exceed the lower limit, which is also a constraint. Fine. So, these two switches are commonly used in abnormal situations. Now, we will discuss the application of this special control scheme, constraint controller, with taking one example. So, we will take a boiler system to discuss the application of this switch. We will take the example of a boiler system. So, water enters at the bottom, feed is water and product is the steam. This is a steam boiler. Fine. So, water is introduced here. Now, for producing steam from water, we need a heating medium which is passing through this coil. This is heating medium which is supplying heat, and this is indicating the water level. This is the water level. This is the discharge line. A control valve is installed in the discharge line. Fine. So, this is the schematic of the process. Now, we wish to include the control scheme. So, first a pressure transmitter is installed, employed to measure the steam pressure, then a pressure controller, here we use one switch, that is LSS. We will discuss why we have selected LSS. Another control scheme is also employed to maintain the liquid level. So, for that we need to employ one level measuring device, that is LT, then one level controller, then the controller signal goes to LSS. LSS output is implemented through the control valve. Fine. This is the constraint control for a boiler system. Fine. So, what is our primary control objective? Our primary control objective is to maintain the pressure of the steam. So, our primary objective is to use a pressure control loop for maintaining the pressure of the steam. Suppose this is loop 1 and this is loop 2. Fine. So, the steam pressure is controlled by the use of a pressure control loop. This is the pressure control loop, I mean loop 1. So, primary objective is to maintain the pressure by the use of loop 1. At the same time, it is required to maintain the liquid level, so that this heating coil is immersed in liquid, in water. So, along with the control of the pressure, it is required to maintain the liquid level, so that this heating coil is immersed in water. Fine. If it is not immersed in water, this coil burns out. So, our another objective is we need to maintain the liquid level. I mean, liquid level should not fall below a lower limit. Liquid level should not fall below a lower limit. Purpose is to keep the heating coil immersed in water. Purpose is to keep this heating coil immersed in water, otherwise the coil burns out. Fine. So, our purpose is to maintain the lower limit for the liquid level. So, which switch we can select? LSS, because it prevents to exceed the lower limit. Therefore, we have selected here LSS. Now, we will consider one situation, how it functions. We will consider one situation. Suppose the liquid level falls below the lower limit. Suppose the liquid level falls below the lower limit. Accordingly, the level controller reduces its output. Fine. If the liquid level falls below the lower limit, the level controller reduces its output to close the valve. So, the control action taken by level controller, that is, level controller reduces its output to close the valve. This is the action taken by level controller. Fine. This is the situation, the liquid level falls below the lower limit. This is the action taken by the level controller. Now, can you explain it, why the level controller attempts to close the valve? If the valve is closed, what happens? The pressure inside the boiler increases. Pressure inside the boiler increases. So, what about the boiling rate? boiling rate decreases, if boiling rate decreases, the liquid level starts improving. If boiling rate decreases, then liquid level improves. Agree? Therefore, the level controller reduces its output to close the valve. Fine. It closes the valve because it exceeds the lower limit. So, therefore, the crucial action is required to take from the level controller sides. So, this is a situation and corresponding action taken by the level controller. Now, I am just trying to highlight the steps. Initially, the pressure controller is in action. Initially, the pressure controller or pressure control loop is in action. Then the water level falls below the lower limit. Water level falls below allowable limit. This situation we have considered. Then level controller reduces its output to close the valve. Fine. Now, when the level controller's output drops below the pressure controller's output, the LSS selects the level controller's output signal. This is very important point. If level controller output falls below the pressure controller's output, then LSS selects the lower value. LSS selects the level controller's output. So, you see previously the LSS, this is LSS, previously the LSS selects pressure controller output. Now, as the liquid level falls below the allowable limit, the level controller's output reduces, and when the level controller output falls below this pressure controller output, the LSS select this lowest amount, I mean level controller's output. So, we can say that the level controller overrides the pressure controller. We can say that the level controller overrides the pressure controller. Fine. Therefore, this controller is also called override controller. Previously, we discussed the reason to call it constraint controller, and this is the reason to call it override controller. Fine. Level controller overrides the pressure controller. So, in this example, we have discussed the application of LSS. LSS selects basically the lower output signal. For the case of HSS, the fact is opposite. HSS selects the higher output signal. Fine. So, this is about the constraint controller. Next, we will discuss another advanced control scheme, that is split range control. Split range control. We discussed the cascade control scheme previously, and in the cascade control scheme there was more than one measurement, but one manipulated input. For the cascade control scheme, more than one measurement and one manipulated variable are involved. But for this split range control, the fact is opposite. One measurement, but more than one manipulated variable involved. For split range control, one measurement, which is basically the controlled output, or you can say controlled variable, and more than one manipulated variable are involved. Fine. This split range control provides added safety and operational optimality. This split range control provides added safety and operational optimality, and these controllers are not very common in chemical engineering. Fine. Split range controller is not very common in chemical engineering. So, we will discuss the concept of split range control with taking one example. We will take one example to discuss this split range control. We will take a non-isothermal batch reactor to discuss this control. Non-isothermal batch reactor. In this non-isothermal batch reactor, the temperature varies with time. Fine. The specified temperature program is given as specified temperature program is given as the batch reactor starts, I mean at the beginning of the batch operation, it operates at 15 degrees Celsius. At the beginning of the example operator, the temperature is 15 degrees Celsius, and at the end of batch operation, the temperature is 100 degrees Celsius. So, obviously, the temperature changes with respect to time in the example batch operation, and it is common for batch operations. So, if we want to maintain 15 degrees Celsius or near to that temperature, we need to use one cooling medium, and if we want to maintain 100 or nearby temperature, then we need to use one heating medium. So, here basically cooling medium is cooling water, cooling water can be used as cooling medium, which is available at 5 degrees Celsius, available at 5 degrees Celsius. So, cooling water can be used as cooling medium, which is suppose available at 5 degrees Celsius. Similarly, as heating medium, steam can be used, which is suppose available at 180 degrees Celsius. Fine. So, these are the two medium which can be used to maintain the temperature of the example non-isothermal batch reactor. Now, we will try to configure the split range control for this example system. This is the schematic of the non-isothermal batch reactor. This is jacketed batch reactor. Fine. One valve is used for cooling medium and another valve is used for heating medium. Now, the split range temperature controller can be used to manipulate the cooling water as well as the steam. SRTC is the split range temperature controller. Fine. This is the jacket temperature Tj. So, we need to give the set point value of jacket temperature Tj. Tj is the jacket temperature and Sp has been used to represent the set point. Now, the control action directs to manipulate the steam and this is also used to manipulate cooling water. Then this action in combined form is implemented. Fine. So, this is the split range temperature control for a non-isothermal batch reactor. This is the jacket temperature which is measured and this the set point of the jacket temperature is also supplied to this split range controller. Then this controller manipulates both steam as well as cooling water for maintaining the temperature throughout the batch operation, which varies from 15 to 100 degrees Celsius. Fine. So, this is the split range controller and this controller is used for broad span temperature control of small plant. This is used for broad span temperature control of small plant or pilot scale plant. This is also used for year bound heating and cooling of office buildings. This is also used for year round heating and cooling of office buildings. This is also used to control pH in wastewater treatment plant. Control pH in wastewater treatment by manipulating both acid and base. This is also used to control pH in wastewater treatment by manipulating acid and base. Fine. So, these are the typical examples of split range control scheme. In the next we will discuss another advanced control scheme, that is feed forward control scheme. We have started feedback control scheme like P, PI and PID controllers. So, now we wish to discuss another control scheme, that is feed forward control scheme. So, before discussing this feed forward control scheme, we are interested to know the limitations of feedback control schemes. Fine. Then we will proceed to discuss this feed forward control scheme. So, what are the limitations of feed forward control scheme? Sorry, limitations of feedback control scheme. This point we wish to discuss. So, for that we can take one example like a heating tank system, which we discussed earlier. So, we will take a heating tank system to observe the limitation. Feed is entering at a flow rate of Fi with temperature Ti. The product is coming out at flow rate F and temperature T. A heating medium is used to maintain the temperature. Suppose that heating medium is steam, which has the flow rate of Q. Fine. We wish to discuss the limitation with this example, taking this example. So, what is the control objective? Control objective is to maintain temperature at its set point value. So, we can say that temperature is the controlled variable and corresponding manipulated variable is steam flow rate, that is Q. Fine. Now, we wish to employ one feedback control scheme. So, we can configure the feedback control scheme now. First, we need to measure the temperature. by using a temperature measuring device denoted by Tt. Then that measured signal is compared with set point value, then this signal is used to calculate the control action, and then this action is implemented through the control valve. Fine. So, this is the feedback control of the heating tank system, feedback control configuration for the heating tank system. Now, you see here we have used one controller, that is TC. Suppose this is a PI controller. The temperature controller which we use to maintain the temperature is suppose a PI controller, that is a feedback controller. Now, how can we write the what will be the equation for this PI controller? Manipulated variable is Q. So, Q is equal to Qs plus Kc multiplied by error plus Kc divided by tau I integration of error dt. This is the temperature controller equation. Fine. Now, in this equation you see Qs, Kc and tau I are constant parameters. In this PI controller equation, Qs, which is the bias signal, Kc is the proportional gain and tau I is the time constant. These three are constant parameters. Fine. Last two are the tuning parameters. Now, Q changes with the change of which variable? Error signal. So, we can say that the Q changes only if error, that means if temperature changes, because T set point is again the constant. Q changes only if error, that means only if the temperature changes. Fine. So, what do we want to say that this feedback control scheme takes action only the temperature change is detected. The feedback control scheme takes action only the temperature change is detected, otherwise it cannot take action. Anyway, we will consider one situation to elaborate this. Suppose there is a change in Ti. Ti is a disturbance variable. There is a change in Ti. You see, in this example, Ti is a disturbance variable. Initially, the process is at steady state. Now, we are considering a situation that is there is a change in Ti. Suppose Ti has increased. suppose Ti has increased. So, it will affect the temperature. In the next step, we can say that it affects the tank temperature. Agree? What will happen? Temperature will increase or decrease? Temperature will increase. So, what about the value of epsilon? Value of epsilon changes, fine. So, basically this error signal decreases and it becomes negative if initially the process is at steady state, fine. At steady state error is 0 because T set point and T both are equal. Now, if temperature increases, then this the value of epsilon becomes negative. Then the controller will take action because error signal has changed. So, according to this equation, if error the value of epsilon changes, then Q changes, fine. So, we can say that in the next step controller takes action. How? Q decreases or increases? Q decreases. So, you see the controller acts after the effect of a disturbance has been felt by the process. The controller acts after the effect of Ti has been felt by the process. Agree? So, it is not possible to avoid the impact of Ti by the use of feedback controller. It means that the perfect control can never be achieved by the use of feedback controller. Perfect control can never be achieved by the feedback scheme. Agree? So, how can we get the perfect control? We can get the perfect control if the controller takes perfect action before the disturbance affects the process, is not it? We can get perfect control if the controller takes perfect action before the disturbance affects the process. So, perfect control we can achieve if the controller takes perfect action before the disturbance affects the process. Agree? So, what is required to do to take the perfect control action? So, for perfect control action, first it is required to measure the disturbance which is affecting the process. This is the first point. It is required to measure the disturbance which is affecting the process. So, what is required to do to achieve the perfect control action? First, it is required to measure the disturbance variable. Fine. First, it is required to measure the disturbance variable. In the next step, the controller should act before the effect is felt by the process. So, for perfect control action, it is required to measure the disturbance, to know the change in disturbance variable, and then the controller should act before the effect is felt by the process. And this is the mechanism of feed forward control scheme. This is the mechanism of feed forward control scheme, and theoretically it can provide perfect control. Fine. So, we can say that the feedback controller acts after the fact in compensatory manner. Feedback controller acts after the fact in a compensatory manner, and feed forward controller acts beforehand in anticipatory manner. So, feedback controller acts after the fact, I mean after affecting the disturbance to the process in a compensatory manner, whereas the feed forward controller acts beforehand in an anticipatory manner. Fine. So, theoretically we can achieve the perfect control from the feed forward controller. Anyway, before going to discuss the theory, we wish to just configure the feed forward controller taking 1-2 examples. Before going to discuss the or before going to analyze this feed forward controller, we just wish to configure the feed forward controller with taking 2 examples. So, first we will take one heat exchanger. This is a heat exchanger. This is process stream. And this is the output of the process stream. Here one heating medium is used, that is steam, for maintaining the temperature of the process stream. Fine. Now, for the feedback controller, the controlled variable is usually measured, but for the feed forward controller, the disturbance is measured. For feedback control scheme, the controlled variable is measured. It is very obvious if you see the equation of any feedback controller like P or PID. Fine. And feed forward controller, the disturbance is measured. Fine. Now, for this heat exchanger, our control objective is to maintain the temperature of the process stream. Our control objective is to maintain the temperature at its set point. What is the manipulated variable? Manipulated variable is steam flow rate. This is the manipulated variable. What are the disturbances? One is process stream flow rate, another one is process stream temperature Ti. So, flow rate and temperature Ti, these two are the disturbance variables. So, we can use one measuring device for the flow rate measurement and another measuring device for the temperature Ti. So, this is for F and this is for Ti. Then one feed forward controller. Block can be included and then this control action is implemented through this control valve. Fine. So, two disturbances are involved in this process and they are measured, then that measured signal go to this feed forward control block and then the control action is calculated and that is implemented through this final control element. So, this is the feed forward control scheme for this heat exchanger. Another example we can take, that is a distillation column. One control valve is employed for reflux rate. This is reflux rate. And another valve is employed for heating medium. Fine. So, this is distillate which has the flow rate of D and composition of XD, that is mole fraction basically, and in the bottom loop the flow rate is suppose B and composition is XB. Feed is introduced here with flow rate F and composition Z. Feed flow rate is F and composition is Z. So, what is the control objective? The control objective is to maintain XD at XD set point, similarly XB at XB set point. Control objective is to maintain the product quality at the top as well as at the bottom. So, what are the disturbances involved here? One is feed flow rate, another one is composition. So, we can use flow measuring device FT and composition measuring device CT. Then one block is included for feed forward controller. Fine. For this top loop XD, the manipulated variable is reflux flow rate R, and for the bottom loop the manipulated flow rate is manipulated variable is QR. QR is basically the reboiler duty. Then this is implemented for QR, and another one is for R. Fine. So, control objective is to maintain XD at XD set point, XB at XB set point. Disturbances are F and Z, and manipulated variables are R for XD and QR for XB. So, this is the feed forward control scheme for the distillation scheme. In the next class, we will discuss the theory involved with this feed forward controller. Thank you.